Good morning to everyone. My name is Akash. I am currently pursuing my BTech 4th year Mechanical Engineering from SR Institute. Today I want to discuss a topic about EV propulsion configuration with the single and multi-motor configuration and also superconducting magnetic energy storage. First let's start with the overview. So where these concepts fit in an EV? Energy source battery to power electronics and motor configuration to wheels. So in single motor, one traction motor supplies vehicle propulsion. In multi-motor, two or more motors provide distributed traction. SMES, so storage managed energy system, stores electrical energy in a superconducting magnetic field. Key focus, torque control, efficiency, fast power response and energy management. Now let's see about single motor configuration. So in this we will provide only one motor depending on the vehicle size and application of the vehicle. So first the battery where supplies electric current and inverter to motor. The motor supplies to gear to differential and finally to wheels. One electric motor provides the required traction power. Power electronics control motor voltage, current and torque. Mechanical transmission and differential distribute power to drive wheels. Simple architecture makes it attractive for many passenger EVs. So in single motor configuration, only one motor is provided because we need less power and depend on the vehicle size and type of the vehicle, only one motor is provided. And by providing only one electric motor, the advantages are simple, lower cost, easy control, easier maintenance. And limitations are less individual wheel control, single point propulsion dependence. Multi-motor configuration. So in multi-motor configuration, two or more motors are used for propulsion. So battery or direct current bus to power electronics, motor one front axle and motor two rear axle. Independent motors allow electronic torque distribution. Two motor systems can provide all-wheel drive. Four motor systems can control each wheel independently. Useful for traction, acceleration, cornering and regenerative braking. So by implementing the two or more motors, the torque and the speed improves, but the efficiency decreases. Types of multi-motor arrangements. In two motor, so one motor is provided on the front axle and another motor is provided in the rear axle. In four motor, one motor per wheel. In wheel motor, motor integrated near wheel. So in two motors, commonly one motor drives each axle. In four motor, each wheel can receive independently controlled torque. In wheels, so reduces conventional mechanical drivetrain components. Trade-off. More control flexibility comes with a higher system complexity. Comparison between a single versus multi-motor configurations. So there are three types: feature, single motor and multi-motor. So in single motor, one motor is used, and in multi-motor, two or more motors are used. Coming to the cost, single motor cost is low and multi-motor cost is high. Control, simpler, more complex, and for single motor torque distribution is mostly mechanical, and in multi-motor configuration the torque distribution is electronic independently. AWD, so it needs additional drivetrain naturally supported for multi-motor. Wheel controlling is limited for single motor, and for multi-motor wheel control excellent. Vehicle dynamics, for single motor it represents moderate flexibility, and for multi-motor high flexibility. Superconducting magnetic energy storage. So SMC stores electrical energy directly in the magnetic field of a superconducting coil. Unlike a battery, the storage mechanism is electromagnetic rather than chemical. A superconducting material carries current with extremely low electrical resistance below its critical temperature. SMEC is best suited to high power rapid response applications. So this is the key idea or key formula. E equals to half L I square, and the advantage is fast response, high power, long cycle potential. These are the main components of an storage magnetic energy system. Superconducting coil, it means stores energy in the form of magnetic field. Cryogenic system, which keeps the coil below critical temperature. Power converter, so controls energy flow between a storage magnetic energy system and electrical system. Control and protection, manages charging, discharge and safe operation. So how the working of storage managed energy system? Charging. When the vehicle is charged, the power converted to superconducting coil and the magnetic energy. This is the discharging position. So stores magnetic energy to power converter and finally electric load. Charging increases coil current and magnetic energy. Discharging reduces coil current and reduces electrical energy to the load. The converter controls the direction and the amount of power flow. And I have already mentioned this is the formula equals to half Li square. E stands for stored energy, SI units are joules. L stands for inductance and I stands for current, SI units are amperes. Example, L equals to 2H, I equals to 1000 A, I mean 1000 amperes, that equals to E equals to 1 megajoules. So comparison between battery and storage magnetic energy system, there are three important things. Parameter battery SMES, storage principle for battery we use chemical, and for storage magnetic we use magnetic. Response fast, extremely fast. Energy conversion, electrochemical, electromagnetic. Cycle life finite, degradation. For SMES potentially very high. And coming to the cooling, battery normally nano-cryogenic and for SMES cryogenic. Cost generally lower for battery and high for SMES. Best suited for energy storage systems, and for SMES we use high power fast response support. These are the advantages and the limitations of SMES. Advantages: very fast response, high power capability, high efficiency potential, excellent for power quality support, high cycle life potential. And limitations of SMES is high capital cost, cryogenic cooling required, complex power electronics and control, strong magnetic field requires protection, less suitable for a long duration energy storage. SMES, I mean, if we provide SMES in electric vehicles, first there will be battery, and after DC, I mean direct current bus, and then to inverter, motor, and also SMES to fast power buffer. So by providing SMES in electric vehicles, you can provide rapid power during acceleration, and also it absorbs high regenerative braking power, and it may reduce peak current demand on the battery. And the practical challenges are cooling, weight, volume, cost, and magnetic field management. SMES and regenerative braking. This is the flowchart of the SMES and regenerative braking. Vehicle kinetic energy goes to motor in generator mode and it transfers to electrical energy, and the waste energy stores in storage energy system. During acceleration, SMES can rapidly return stored energy to the drivetrain, and the key benefit is fast absorption and release of high power energy. These are the key takeaways. Single motor means simple, economical, and easy to control. And for multi-motor, independent torque control and AWT capability and improved dynamics. SMES stores energy in a superconducting coil in the form of magnetic field. SMES equation E equals to half Li square. SMES strength, very fast response and high power. SMES challenges, high cost and cryogenic cooling. For EVs, SMES is the best viewed as a rapid response power buffer rather than a replacement for the main battery. Thank you.